The program of the webinar. I will start from work conditions of engine bearings. I will explain, not explain, remind you the the principles of hydrodynamic lubrications and also the requirements for engine bearing materials. Then I will continue with the typical failures of engine bearings, such as material fatigue, wear, seizure, cavitation erosion, and corrosion. And the last section is features of engine design and their effect on engine bearings. I will talk about the turbocharging, compression ratio, gasoline engine versus diesel engine, oil viscosity, the engines called homogeneous charge compression ignition, a new development, low rigidity of bearing housing and crankshafts, and the last, emission reduction. The first section is work conditions of engine bearings. Okay, engine bearings are hydrodynamic bearings, and which means that the bearing and shaft surfaces are separated by oil film, continuous and constant oil film. This is generally correct, but it doesn't correct always. So, but in principle, as I said, it's hydrodynamic bearing. In this image, you can see a hydrodynamic bearing and the shaft rotating in a clockwise direction. Oil separating the bearing and shaft is depicted in orange color. You see that the bearing and the shaft surfaces are separated with the oil. Hydrodynamic bearing is a bearing operating with hydrodynamic lubrication. And when shaft rotates, it causes the oil to flow around the bearing and out of it in this direction. I would say that hydrodynamic bearing works as an oil pump. Oil is being continuously fed into the bearing and continuously leaking out of the bearing. The external force, F, displaces the journal from the shaft, from the bearing center. The shaft surface is getting closer to the bearing surface. The shaft displacement forms a convergent gap or convergent wedge, this one, with the angle alpha between the bearing and shaft surfaces. The oil pressure in the convergent wedge increases in the rotation direction. And it reaches maximum somewhere here, where the thickness of the gap between the shaft and the bearing surfaces reached the minimum value. This gap is called minimum oil film thickness, or MOFT, minimum oil film thickness. The oil pressure creates lift force. The pressure that rotating shaft generates, it creates a lift force separating the shaft from the bearing surface. The lift force counteracts the external force F. They are equal, but they are directed in opposite directions. The lubricant is enforced to squeeze through the gap between the bearing and shaft surfaces. Together with the lift force, the hydrodynamic friction force is generated. The balance between the forces determines the final position of the shaft and the value of minimum oil film thickness. The value of minimum oil film thickness indicates stability of hydrodynamic lubrication. The greater MOFT, the more stable hydrodynamic regime of lubrication. So when we design engine bearings, we design them to have the maximum value of MOFT, of minimum oil film thickness. In the bearings of the modern engines, the value of minimum oil film thickness may be as low as 40 micro-inch or 1 micrometer. You can compare this number with the diameter of human hair, which is 2000 micro-inch or 50 micrometers, 50 times thicker than the oil film separating bearing from the shaft. As I told you that engine bearings are hydrodynamic bearings, but they are not always hydrodynamic. If the shaft is perfectly round, look at this image. If the shaft is perfectly round, straight, and parallel to the bearing surface, if the bearing is perfectly round and straight, if the oil is clean, in other words, if the bearing is ideal, then it works in the purely hydrodynamic regime of lubrication, this one. So if so, the engine bearings maybe the engine bearing material may be just steel because there is no contact between the bearing and shaft material in the ideal bearing. So there is no need to have anti-friction coatings and other anti-friction materials. However, there is nothing perfect in the real world. Unfortunately, or maybe fortunately, the bearing is not ideal. Real bearings are not ideal. The shaft may be non-parallel to the bearing, like here. And then the bearing surface is touched with the shaft at an edge. The shaft bends and touches the bearing surface at two edges, here and here. The oil may contain solid contaminants, abrasive particles scratching the bearing surfaces, like here. Excessive loading or may cause fatigue of the bearing material, like we see here. Roughness of the shaft and the bearing may be higher than thicker than the minimum oil film thickness, like here. And then in this case, hydrodynamic lubrication converts to mixed lubrication regime with some metal-to-metal contact. And also the bearing geometry may be not perfect, maybe non-round, out of round, like here, because of inertia forces developed in the connecting rod, or because of thermal distortion of the housing of the main bearings, and also some defects of grinding of the shaft may break hydrodynamic lubrication, and the bearing is not perfectly hydrodynamic. Thus, engine bearings sometimes work under the mixed lubrication regime, not purely hydrodynamic. Therefore, the surface anti-friction properties and strengths of the bearing material are important. Now about the bearing material properties. There are two groups of the bearing material properties. The first group relates to material strengths. They are load capacity or fatigue strength, wear resistance, and cavitation resistance. The second group is about the anti-friction properties. These are seizure resistance, conformability, and embeddability. I explained those properties in the previous webinar. The two groups of properties contradict each other. Fatigue strength, wear resistance, and cavitation resistance are attributed to the material strengths, whereas seizure resistance, conformability, and embeddability relate to the material softness. This is illustrated in the graph. The harder the bearing material, this is the hardness, and this is the bearing properties. The harder the bearing material, the higher its fatigue strength and wear resistance, but the lower its seizure resistance, conformability, and embeddability. To achieve the required compromise between the properties, the engine bearing materials are designed to have a composite structure, combining soft and strong materials. The next section is about the failure modes of engine bearings. Fatigue. Fatigue is the most dangerous mode of bearing failure. What is fatigue? If you take a metal part and apply stress to it, which is, if the stress is below the strength of the material, the part will not break and not crack. However, if you apply stress multiple times, let's say 1 million times, the part will crack. This phenomenon is called material fatigue. Fatigue is a failure occurring under cycling loads. Engine bearings experience alternating cycling loading because of the cycling character of the internal combustion process. Fatigue cracks start on the material surface. You can see here the image of the cross section of the bearing material. This on the top you see the bronze layer, and here you see the steel back, and this is the bearing affected with fatigue. Fatigue crack starts on the surface, and then it progresses into the material until it reaches the boundary with the steel back. Steel back is very strong, and fatigue cracks rarely continues through the steel back, but in most cases it changed its direction along the boundary. You see the crack continues along the boundary, and pieces of the bearing material may detach from the substrate. What are the probable causes of engine bearing fatigue? First of all, the wrong selection of engine bearing material. If, for example, the engine is diesel engine with turbocharging, and we select for this engine the upper part of the rod bearing made of steel aluminum material, this material will fatigue because the actual loads in the acting on the connecting rod bearings, upper part of the connecting rod bearings, may reach 100 or even 120 megapascal, and the fatigue strength of the aluminum bearings is only 40 megapascal, so it will definitely fatigue. The next possible cause is oil starvation. When the hydrodynamic regime is broken and there is due to oil starvation, there is a localization of load at a small bearing area, and in this small bearing area, the specific load, which is load divided by the area surface, it may be higher than fatigue strength of the material. Also, the geometry misalignments cause localization of bearing loading and also may cause fatigue. And the last possible cause is engine detonation, when the pressure in the cylinder is much greater than the pressure which should be in the normal combustion process. In this slide, you see examples of fatigue failure of aluminum bimetal bearings. You can see that pieces of aluminum lining flake out from steel back, resulting in immediate engine failure. You see also here and here and here the material missing, the fragments of the lining delaminated and gone. And in addition, in aluminum bearing, excessive loads cause an extrusion of lining material beyond the bearing edges. Like here, you can see that the bearing material extruded out of the bearing edge, and also here. Other examples of fatigued aluminum bearings: missing fragments of the lining, and extrusion, heavy extrusion of the aluminum lining out of the bearing edges. If a bearing is edge loaded, the load is localized at a small area, and the specific load may exceed the fatigue strength of the material and cause its fatigue. You can see here edge loaded bearing with the fatigue area, also here and here and here. In this slide, depicted aluminum main bearings having a fatigue in the lower part. Here, in the lower part, you see missing lining. This is fatigued. These are the fatigued parts. The upper parts also have some distress, but you can see here. But this is not fatigue. These are dents on the aluminum surface produced by the fragments of lining delaminated from the lower parts. A mechanism and appearance of fatigue of bronze lining is similar to those of aluminum. Bronze lining cracks and pieces of it are delaminated from the steel surfaces, like in the bearings in the image, and this causes the catastrophic bearing failure. You see also this bearing where which worked under oil starvation condition, and the load was localized at the bearing center, and this produces fatigue of the bronze lining. Now, fatigue of overlays is somewhat different. First of all, fatigue strength of an overlay depends on its thickness. As it is depicted in the graph, the thicker overlay, this is the thickness of the overlay, and this is the fatigue strength of the overlay. The thicker the overlay, the lower its fatigue strength. That's why in modern engines, particularly in racing engines, the overlay is very thin, much thinner than the bearings which were in use, let's say 50 years ago. Fatigue cracks on the overlays appears as a spider web. You can see here, or in this magnified image, you see the small, thin fatigue cracks. Fatigue of overlay is a relatively slow process, and it does not cause immediate failure. However, fatigue may lead to partial flaking of the overlay, followed by seizure or fatigue of the copper-lead underlying copper-lead lining. The next failure mode is wear. There are 3 levels of bearing wear. Accelerated wear, when the bearing is not overheated and it has a shiny surface, like here. Heavy wear with signs of overheating or blackening, partial melting of the overlay, and exposure of the bronze lining, like here. And severe wear and torn surface with heavy overheating, melted overlay, and melted lining material, like here. The possible causes of wear, First is insufficient oil supply or oil starvation, when there is no hydrodynamic lubrication and there is a metal-to-metal contact between the bearing and the shaft surfaces. The second is breaking the oil film due to fatigue. Fatigue also breaks oil film and then starts metal-to-metal contact. Geometrical irregularities such as edge loading or non-parallelism, rough surface or rough bearing surface or rough shaft surface, and contaminated oil, when oil contains abrasive particles which produce scratches. Another example of bearing affected with a heavy abrasive wear you can see in this image. In this slide, you see bearings affected with abrasive particles circulating in oil. Scratches on the bearing surfaces can be observed here and here. And pay attention on this image. You see the abrasive particles embedded into the bearing surface. When they embedded into the surface, they are neutralized, but of course, bearing cannot neutralize all abrasive particles in the oil. Edge loading may produce local wear at one or at both edges. You can see here the wear at one edge, here at this edge and this edge, and also here one edge. The edge loading may be a result of distorted shaft, like here, or distorted housing. Edge wear may play a positive role when the bearing profile adapts to the bent or non-parallel shaft. The surfaces become conformed, the surfaces of the shaft and the bearing become conformed due to the local wear of the bearing material. Here you see a conformed bearing having edge wear at both edges, and the wall thickness at the edges was reduced by 8 to 12 microns as compared to the central area. And after that, the bearing obtained the profile which conforms the profile of the bent shaft, and after conforming process, the bearing continues to work in hydrodynamic lubrication regime. Sometimes, in some bearings, the inner profile is designed and fabricated with edge ramps, like here and here. The bearings that you see in this image, these are aviation main bearings, and those ramps facilitate or make easier the conforming process. Seizure is a physical joining, metallurgical joining, like friction welding of the bearing material with the shaft material, when metal-to-metal contact between the surfaces occurs under high load. The bearing material in seizure, the bearing material is transferred. It sticks to the shaft and transferred to the shaft, and in each rotation, the amount of transferred material on the shaft increases like snowball. Seizure is a catastrophic failure. Cavitation erosion. Cavitation is a common phenomenon in hydrodynamic systems such as propeller or fluid pumps, etc. Also, it is common in engine bearings, because engine bearings is also hydrodynamic system. Cavitation in a hydrodynamic bearing occurs when the load applied to the bearing fluctuates at high frequencies or at high RPM speed. the oil pressure instantly falls, causing formation of cavities in the oil due to fast evaporation, like boiling. When pressure rises again, the vapor cavities or cavitation bubbles contract at high velocity, and such collapse of the bubbles result in impact pressure waves which may erode the bearing material. Cavitation erosion is more typical for high-speed engines like racing engines working at 10,000 RPM, up to 10,000 RPM. Cavitation erosion may occur in common engine bearings having obstacles on the surface, such as holes, oil pockets, etc. You see here two bearings with the oil hole, and you see the area affected with the cavitation erosion around the oil holes. This slide depicts a spun bearing. Friction between the shaft and the inner bearing surface produces friction force trying to spin the bearing in the housing. The bearing does not spin if the counteracting friction force between the bearing back and the housing surface is sufficiently high, and then the friction force on the outside of the bearing surface counteracts the friction force inside the bearing surface. The friction force between the back and housing is determined by the press fit of the bearing in the housing. The parameter determining the press fit is called crash height. If the press fit is too low, the bearing spins. And of course, this is catastrophic failure. And the corrosion of bearing materials. Corrosion of bearing materials is relevant for leaded materials. Lead is excellent anti-friction material, maybe the best metallic solid lubricant. And lead has been very popular since 150 years ago. So lead is excellent anti-friction material, but lead is susceptible to corrosion in acidic oils. A trimetal bearing affected with the corrosion of lead in both in the leaded bronze lining and lead in the leaded overlay is depicted in this photo. You see the black spots on the bronze surface, and you see in the cross section image, you see the black corrosion products inside the bronze lining. Oil becomes acidic as a result of fuel dilution, thermal oxidation, and reaction with soot. Now the last section is features of engine design and their effect on engine bearings. The first feature is turbocharging or supercharging. In a combustion process, the ratio between the amount of fuel to no, it's no, it's it is approximately 50. This number is called the stoichiometric ratio. In the internal combustion engine, the amount of air in the cylinder is determined by two factors. The first is the volume of the cylinder, and the second, the pressure of air entering the cylinder in the intake stroke. So if the pressure is proportional to the number of molecules of oxygen which are required for combustion process. In the turbocharged engine, the air pressure is greater than in the normally aspirated engine. If, for example, the turbocharged pressure is 2 bar, instead of 1 bar in the normally aspirated engine. This means that the amount of oxygen molecules is twice as much as in the atmosphere aspirated engine. Therefore, the amount of fuel which may be burned in this cylinder is also twice as much as in the normally aspirated engine. And the amount of energy generated by the engine in one cycle is twice as much as in the atmosphere aspirated engine. Normally, more energy produces higher pressure and higher temperature of the combustion gases. The higher the gas pressure, the greater the loads acting on the bearing, because the gas pressure generates a force acting on the piston, and this force is transmitted through the connecting rod to the upper rod bearing and to the lower main bearings. So if the engine is turbocharged, the bearing material should have a higher fatigue limit because it works under higher loads. In addition, higher loads result in a reduction of the minimum oil film thickness and more frequent metal-to-metal contact, faster wear, and higher probability of seizure. The bearing materials should combine a higher load capacity with enhanced anti-friction properties. The next feature is octane number and compression ratio. Thermodynamic efficiency of an engine, of an internal combustion engine, is determined by the compression ratio. It is worth increasing the compression ratio as much as possible in order to increase the efficiency of the engine. However, too high compression ratio causes the engine detonation or knocking when the charge burns in an uncontrolled explosive spontaneous mode instead of progressive flame propagation. Special additives in fuel are added to suppress detonation at high compression ratios. An octane number is a measure of fuel's ability to withstand compression without causing engine detonation. Thus, the engine working with higher octane number, with fuels having a higher octane number, are capable of higher compression ratios. The higher the compression ratio, the higher the cylinder pressure, because the gases are compressed more, and the greater the bearing loading. Now let's compare the bearing conditions in two types of engines, a petrol engine and a diesel engine. In contrast to the petrol engine, which is spark ignited, the fuel-air mixture in diesel engine is compression ignited. High pressure and high temperatures are required for compression ignition. Therefore, the compression ratios of diesel engines are higher, normally 16 to 20. Accordingly, the cylinder peak pressures in the diesel engines also higher. The combustion pressure is transmitted by the piston and the connecting rod to the bearing. And in addition, the most modern diesel engines are turbo aspirated, which also increases the load acting on the bearings. The upper halves of the rod bearings working in diesel engines are made of special high-strength materials. The adverse effect of very thin minimum oil film thickness, such as frequent direct contact with the shaft and the risk of seizure, can be reduced by using anti-friction coatings. Now about the reduction of oil viscosity. If you look at this chart, you can see the trend of using low viscosity oil grades. It's from the year 2000 to 2030. And the engine designers persistently reduce the oil viscosity grade in the newly developed engines. Their motives are clear. The energy losses in the hydrodynamic bearings are determined by oil viscosity. The lower oil viscosity, the lower the energy losses, and the lower fuel consumption, and the lower the emission of CO, NOx, and CO2, the emission gases. But what about the bearings? In this slide, you see a comparison of the effect of two oils. The left graphs are about the oil 15W40, and the right graphs about the oil 0W10. The upper two graphs compare the effect of viscosity on energy loss at three different rotation speeds. This axis is power loss, and this is the axis of oil clearance. So you can see that the maximum power loss in the 15W40 oil in the bearing is about 800 watt. But if you use in the same bearing the oil 0W10, the maximum power loss is 490 watt. On the other hand, if you look in the bottom at the bottom graphs, which explains the effect of oil clearance on minimum oil film thickness for the oil 15W40 and for the oil 0W10 at three different rotation speeds. You can see that the values of minimum oil film thickness is in the low viscosity oil is between 15 to 34 micro-inch. If you compare it with the oil 15W40, you see that minimum oil film thickness reaches 50 micro-inch, so it is greater, and the lubrication regime at high viscosity oil is more stable. And the effect of the low viscosity oil on the bearings is excessive wear and more probable seizure due to more frequent events of metal-to-metal contact because of low values of minimum oil film thickness. Now the homogeneous charge compression ignition. This is a relatively new engine, but I think it is interesting to look at this engine. According to the forecast, some forecasts, in 2028, a production of those engines may reach 12 billion US dollars. If you compare two different engines, diesel engine and petrol engines, you can see that diesel engine, in the diesel engine, the charge is stratified. It is not homogeneous. There is a area of or space of rich mixture and lean zones. And the ignition is compression ignition, which is spontaneous, and the combustion is progressive combustion. If you look at the petrol engine, the charge is homogeneous, and the ignition is spark ignition, and again, it is progressive combustion. Now, the HCCI engines, it's a kind of engine combining features of both petrol and diesel engines. the fuel-air mixture is homogeneous, like in petrol engines, but HCCI engines are compression ignited, like diesel engines. The combustion process is volumetric, not progressive. I would say that combustion of HCCI engine is a kind of controllable detonation. And because of this specific combustion mode, which is similar to detonation, and high compression ratio, about 15-16, HCCI engines develop high combustion pressures in the cylinder, which is again transmitted to the bearings, and the loads acting on the bearing are very high. And also the minimum oil film thickness is very thin. So there is a risk of fatigue, and there is a risk of excessive wear and high probability of seizure. The next feature of the modern engines is low rigidity of bearing housing and crankshafts. Low rigidity of modern engines is a result of both compact design, downsizing of the engine, and high combustion pressures and forces generated by the engines. Bent crankshafts and the mechanical and thermal distortions of the bearing housings induce misalignments and disturbances of the bearing geometry. And the hydrodynamic lubrication breaks frequently, causing edge loading, edge wear, and more possible fatigue or seizure at the areas where the shaft touch the bearing surface. The next slide is emission reduction. Emission reduction is the highest priority item for engine designers. Emission reduction, I can say that emission reduction is the sacred cow of engine designers. It's in the first priority, the second and third priority. Two major developments have been made to reduce engine emission. The first is engine downsizing, and the second, start-stop system, which is implemented in internal combustion engines, in hybrid engines, and in plug-in engines. Let's consider the effects of them on the bearings. First, the engine downsizing. When the engine dimensions and weight are reduced, the crankshaft is reduced accordingly, the crankshaft dimensions. In the shorter, the crankshafts are shorter and they have lower diameters. In the shorter crankshafts, the spaces for the bearings are also shorter. The bearing diameter are also smaller. So the combustion pressure, on the other hand, are increased because of the enhanced engine efficiency. Thus, higher forces developed in the cylinder act on a lower bearing surface, which results in a sharp increase of the specific load. I remind you that specific load is the force acting on the bearing divided by the bearing area. Bearing area is the bearing diameter multiplied by bearing length. So if the bearing area is smaller and force is greater, when we divide the force by the bearing area, the specific load increases considerably. And at the same time, the value of minimum oil film thickness decreases. So higher loads may cause fatigue, like you see here. Thin oil film may cause seizure and excessive wear. In the start-stop engines, the conditions of low rotation speed are more frequent because if you look at this graph, you see that you see the blue curve relates to the low rotation speed, and at some oil clearances, the value of minimum oil film thickness at low rotation speed becomes zero. So if we reduce the rotation speed below 1000, let's say 400 rpm, the value of the minimum oil film thickness is zero at any oil clearance. So fortunately, it occurs at very low loads. But anyway, there is metal-to-metal contact in every event of switching the engine or shutting down the engine. And the effect of this is excessive wear, like you see here. And conclusion. From all considerations of the modern features of the engine design, we can define two challenges for the bearings. The challenge A, increase of specific load, and the challenge B, less stable hydrodynamic lubrication because of a decrease of the minimum oil film thickness. In order to overcome the challenge A, the bearing material should be harder. In order to overcome challenge B, the bearing material should be softer. You remember this graph. So in the modern bearings, in the modern engines, the bearings should be harder and softer. It sounds paradoxical. The solution of the contradictory requirements is development of bearing materials having sophisticated composite structure which combines strong materials with multi-layer anti-friction coatings. Thank you for your attention.